Hi, Chiara. Vittorio, questo senza... Hi, how are you?
Fine,
Come
thank you.
questo? No, è molto meglio.
Ciao Chiara.
Ciao, ciao.
Ciao. 2 minuti e iniziamo, faccio 5 minuti di introduzione e poi ti passo la parola, introduci il collega Liviu e poi partiamo con la parte plenary e poi quindi con la sessione, d'accordo?
Perfetto.
E Filippo?
Ciao. Ciao Chiara.
Ciao.
Ciao.
Tutto bene?
You are in Norway?
Yes.
Okay.
Yes.
So I'm in Italy.
Yeah, I know. How is the weather? Nice?
Beautiful.
Ah, good.
Ok.
So I have 12 minutes.
All the time you wish.
Oh, okay. Okay. Because you told me that it's a short presentation.
You have a half an hour short presentation and question and answer, so you can take your time. Okay. So don't worry, you are the player. So thank you so much for being here. Okay. Okay. Ladies and gentlemen, good morning. Welcome to this official opening. And first of all, I wish to warmly thank all the speakers, all the chairmen for their contribution to the success of this event. And I wish also to warmly thank our sponsors, Step Lab and MTS, that supported us in the organization of this event. Well, today we will have a very long day with many interesting presentations, a really interesting plenary lecture from Professor Livio Marsavina, and it is my pleasure to introduce you my dear friend Chiara Bertolin from Norway. We have this strange situation, and thank you so much, Chiara, for your help. So please enjoy your chair.
Thank you very much, Francesco. Good morning to everyone. Welcome to the audience and the speaker of the section 5th of the 26th International Conference on Fracture and Structural Integrity. In this section, beside the plenary talk of Professor Marsavina, we have other 6 presentations. Before to leave the stage to Professor Marsavina, I shortly recall the format of the section. Each speaker, except Professor Marsavina, has 10 minutes time slot available. Within this time, the speaker in 2 minutes, very shortly, will summarize the talk that he or she prepared as video presentation. And then in the rest of the time, the audience may ask a question and start a brief discussion. I kindly ask the speaker and the audience to remain in time, but I will check this time. So I am very glad to introduce the first speaker of the section with an invited plenary talk. And welcome to Professor Liviu Marsavina from the University Politecnica Timișoara in Romania, that will present the assessment of fracture in cellular material. Professor
Sorry.
Marcevina,
Yes. Thank you very much, Chiara, for your kind introduction. I will try to share my screen. So, good morning, everybody. First of all, I would like to thank to organizers for giving me the opportunity to be in Turin. Last time when I was in Turin was in 2005 at International Congress on Fracture, organized also by Politecnico di Torino. I also would like to thank the Italian group of Fracture because after more than 1 year, we can meet again together, part of us physically. So here, the last conference that I participate with many of you was in Athens. It was an event organized also by Italian group of Fracture in February 2020. So before to start my presentation, I would like to acknowledge the contribution of my colleagues from Timișoara, Dr. Radu Negru, Dr. Emanuel Linul, and Dr. Dan Sherban, and also the cooperation with Professor Filippo Berto from NTNU Trondheim in Norway. This presentation represents a tribute to Professor Paolo Lazzarin for his outstanding contribution in the field of structural integrity, but also a very good friend, a very good man who helped a lot of researchers and mostly young researchers. I have many interesting talks with him during the conferences in the past years. Why cellular materials? Cellular materials are widely used now, mostly in civil engineering, in constructions for thermal isolation, but also for packing, for automotive industry, in sport engineering. They have lightweight, high porosity, good thermal isolation, and great capacity to absorb impact energy. On the other hand, they are very good in compression, but they are quasi-brittle in tensile, and they became very brittle in the presence of notches or cracks. So this is the reason that we start to apply the fracture mechanics concepts to this type of materials. What I will show you today, there are 4 different types of polyurethane foams with the commercial destination of Necuron. They are made in Germany by Necumer company. Starting from 100 kilogram per cubic meter density up to 700 kilogram per cubic meter density. You can see here that with increasing the density, the cell diameter is decreasing from 100 microns to around 42 microns. The cell wall thickness are increasing. So what we can see here, at low density, the polyurethane materials show a closed cell structure, while at high density materials, they highlight a porous solid structure. Our previous works show that we can apply the theory of critical distance, and the critical length was related to the cell size. So what we want to show now is that also the average strain energy density approach can be applied for this type of materials, and we replace the ultimate tensile strength of the material with the ultimate tensile strength of a notched component. This was determined by a student from Padua. He was in an Erasmus placement in Timișoara, and we use this type of specimens with notches, and we determine the ultimate tensile strength of notch specimens. The tests were performed in classical manner, so in displacement control with 2 millimeter per minute crosshead speed and at room temperature. So We also using in this presentation I will use only cracked specimens, so the control volume it's circular, and we use the Yoshi-Bash relationship for plane stress condition to determine the control radius. The cracked specimens that we investigated were single edge notch band specimen loaded in 3-point bending, compact shear specimen for mode 2 loading, asymmetric semicircular band specimen for mixed mode loading from pure mode 1 to pure mode 2, and also we use single edge crack specimen loaded in Arcan grips for determining the mixed mode loading in specimens. We use the same testing equipment, the same displacement control, and the tests were performed at room temperature. This is only a summary of the average maximum load for all the tests that we did. Usually we did 4 or 5 tests for each combination, for each mixed mode, and for each type of specimen. Then we try to calculate the strain energy density parameters, the critical strain energy density and the control volume. We try to use to find this using the micromechanical models, which are used to express the property of the cellular materials based on the property of the solid material and on the relative density of the foam. So such relations, micromechanical models exist for Young modulus, for stress strain curve, for fracture toughness. What we did with our experimental data, we found some relations for our particular polyurethane foam, the expression of Young modulus, of notch tensile strength, and of fracture toughness. These values we fitted in the critical strain energy density and the control radius to find these values, and you can see here the results. The strain energy density, it's increasing the density, while the control radius, it's decreasing with increasing the density. We also were look the same like in the case of the theory of critical distance. We look on the relationship between the control radius and the cellular cell size, and we found that the control radius is approximately 5.6 times the cell size, taking into account all span of the densities. Then we perform some linear elastic finite element analysis using Abaqus plane stress conditions. We use the same control radius for all in the first approach for all mixed CTs. So you can see here the distribution of the strain energy density for mode 1, for mixed mode, and for mode 2. This is obtained only by moving, for this type of specimen, only by moving one of the supports, for when it's symmetrically we have pure mode 1, and going to close to the crack. So we have mixed mode, and on one particular position, in this case 2.6 millimeters, we have pure mode 2. We express the results as a square root of the finite element strain energy density to the critical strain energy density. And this was plotted versus the relative density for mode 1, for 3-point band testing, for asymmetric circular band and single edge crack specimen. In mode 2, for compact shear, for asymmetric semicircular band and single edge crack specimen. So and then for the two mixed modes, so we have the different densities, and we have the mode mixity parameter. these results are from asymmetric semicircular band, and these are for single edge crack specimens. We also try to predict the maximum load. So what we do, we change the load. We keep the same control radius, and we found the polynomial equation between the predicted load and the asymmetric with the average strain energy density, and for typical density for the strain energy what we have it, so we predict the maximum load. These predictions works quite well for mode 1 and predominantly mode 1, but it's became the predictions are lower with up to 25% for pure mode 2 and predominantly mode 2, these 2 points. So what we were thinking there to try to change the control radius in order to improve these predictions. This is what we did. So we calculate the control radius for mode 2. We use the fracture toughness results determined on compact shear, and we use ultimate shear stress, which was a proportion from the ultimate tensile stress, and we found a linear relationship between for the control radius relative to the mode mixity. So such a relation, and we recalculate our maximum loads, changing the control radius from pure mode 1 to pure mode 2. So having different values of the control radius. Obviously, the predictions go better, so the relative error in predicting the maximum load decreased for 25% in pure mode 2 to 7.5%. So to conclude, we did some static fracture test of cracked polyurethane foams under different types of mode mixities from mode 1 to pure mode 2. And we assessed the fracture using average strain energy density criteria. The novelty of this study was the link between the strain energy density parameters and to the cellular topology, relative density, and cell dimensions, and to the micromechanical predictions of the mechanical properties of the foam. The volume control for cracked components was represented by a circle with the center at the crack tip for all types of fracture modes. And it was demonstrated that the set parameters obtained from pure mode 1 could be applied successfully for mode 2. But if you want to improve the predictions of the maximum load, we use a linear relationship between the control radius determined with the properties from mode 1 and with the properties for mode 2. And finally, as many papers demonstrated before, so we can say that this approach, average strain energy density criteria, it's an useful engineering tool for assessment of brittle fracture of components made of cellular materials. So I would like to thank you for your attention, and if there are any questions, please. Thank you.
Thank you very much, Professor Marsavina. So is there any question from Turin, from the audience in Turin? Or from the audience online?
Sorry?
Okay, so I have a question, Professor Marsavina. So it's very interesting, this modification that you did of the controller radius to improve the prediction of the maximum load. And the question is, do you expect a different control radius if you change, for example, the type of test, for example, under torsion or under other type of
we
effect?
didn't
Do you
take into
different?
We didn't take
yes,
into
I know, but
mode 3, so the torsion mode, because all our specimens were, let's say, plain specimens loaded in their plane.
Yes, but
probably
as
it
the
could be
research.
Probably could be interesting to think on a 3D, some 3D specimens, and to take into account also the mode 3. I'm sure that if for mode 1 and mode 2 you can find a relationship to tune the control radius, will be the same if you use mode 1 and mode 3, or all three modes.
Okay, so this could be a new topic or progression of your research eventually.
Yeah.
To test mode 3. Okay.
Yes.
And about the thickness effect, in your opinion, is relevant on the test that you perform? Did you consider this thickness effect on your samples? So, because the dimension of your sample.
I couldn't understand, please.
No, is the thickness effect relevant for your test? Did you consider it?
So unfortunately, we could not use for all the specimens different types of thicknesses, because the plates of the material have a particular thickness. So we cannot go for some of them.
Okay.
We cannot go on thicker specimens to investigate this.
Mm-hmm. Understand. So it's a problem of production of the material, and you cannot
This
modify.
is why we assume plane stress and not plane strain, because I think the plane strain conditions was not fulfilled for all our tests.
Understand. Thank you. From the audience, is there any question? Okay, so I thank you very much, Professor Marsavina, for the interesting talk. And also we are a bit earlier respect to the schedule. I think that we can progress with the first talk of the section, short talk.
Okay, thank you. Thank you.
Thank you very much. Thank you. So the second talk, the second speaker is Dr. Costanzo Bellini, research fellow from the University of Cassino and Southern Lazio, from the Department of Civil and Mechanical Engineering, which will present his work on CFRP, aluminum fiber metal laminates, numerical model for mechanical properties simulation.
Good morning. Can you hear me? Okay, thank you. I'm sharing my screen. And is this one. Okay. So, good morning. I'm presenting my work about the numerical simulation of the mechanical behavior of an FML based on composite material, carbon composite material, and aluminum. This work is based on the simulation of the 3-point bending test. That is a typical test carried out on such kind of material. And in particular, we simulated the behavior of both a long and a short beam, because in such manner we were able to simulate both a normal stress state, so tensile and compressive, and a shear stress state in the case of the short beam. The material is in this image. We simulated the material composed by a central metal sheet made of aluminum and two external CFRP layers. that were connected to the aluminum using an adhesive, a structural adhesive. As concerned the simulation, we considered only a quarter of the specimen for the long beam and an half of the specimen for the short beam. The mesh was formed by brick elements, 8 nodes linear brick elements. And the CFRP was simulated as an homogeneous orthotrophic material, while the aluminum as an homogeneous isotropic material. As concerned the boundary conditions, we considered the plane of symmetry by blocking the normal displacement. The loading was simulated by applying a displacement at a fixed speed, at a constant speed, while the support were simulated by impeding the vertical displacement of the nodes where the supports act. As concerned the result, we can see that the numerical simulation, the numerical results are good, and they are replicating the experimental results, both for the long beam and the short beam. Also, the locus of fracture was predicted in a quite good manner, as we can see from this image and from the micrography that were taken on the failed specimens. So thank you for your kind attention.
Thank you very much, Dr. Bellini. So is there any question from the audience online or from Turin? You can also write the question on the chat if you are shy, and I can read it. But I have a question, Dr. Bellini. What happens, because the geometry, let's say, of your beam is quite simple. What can happen if the geometry becomes more complex? Do you expect a similar type of decay and fracture and delamination? Or did you try more complex geometries?
Yes, this is a preliminary simulation, so we have used this simple geometry, but I can expect more or less similar behavior also for bigger geometry. Usually these materials are used for panels, so I can expect the lamination, as in the case of the short beam, if the stress scheme is similar to that one of the short beam, or I can expect also a failure of the fiber on which is acting a tensile stress. Usually, I think that this is the two main yes, the two main mode of failure.
And is there any size limit to pass from one typical type of failure or the typical delamination?
Usually it depends on the ratio. In the case of the three-point bending, it depends on the ratio between the thickness and the distance between the support.
Okay.
It's the contrary.
So you can simulate when you will have a specific.
Yes, we can expect one, so the shear stress or the tensile stress, depending on this ratio.
Okay, this is very interesting. Thank you.
You're welcome.
Other question from the audience? Okay, so today the audience is very quiet, but thank you very much, Dr. Bellini, for your speak and your talk. So we can progress further with the third talk. I can ask you to stop the sharing, yes. So the next speaker is Fabio Alberti. a PhD student from the University of Messina, from the Department of Engineering, Messina in Italy. And the work of Alberti is titled Tribological Characterization of a hip prosthesis in Si3N4TIN ceramic composite made with electrical discharge machining.
Good morning.
Good morning. You can share the screen if you need.
Okay, thank you. Okay. Did you see?
Yes.
Okay, perfect. Okay, first of all, good morning and thank you a lot for the introduction. Yes, this work basically is, as you said previously, regards the tribological characterization of eye processes, and in particular, we are focusing on the wear process and the friction between the acetabular cup and the femoral head of eye processes. In particular, all the process is made in a ceramic composite, so we have a ceramic matrix which is doped with metal, and this dopant allows the use of the ADM technique, which basically is an unconventional machining technique, which is very powerful to reach very complex geometry and reaching also very good roughness, etc. As you see here, is a collaboration between the University of Messina and also the Alimep Society, represented by engineer Lorenzo Scappavicci. So the first step of the work is the evaluation of the friction coefficient between for the ceramic on ceramic coupling, and the friction coefficient is evaluated through the pin-on-disc tribological test. So basically, the first step is the specimen preparation. So with the DM technique, obviously both the disc and the pin are realized in this ceramic composite and with the electrical discharge machining, and through from the tribometer is possible to evaluate the friction coefficient. In particular, we made two tests that I called in the presentation test A and test B. This is very important because one of the inputs of the finite element model that we build later is obviously the friction coefficient. So we need to know exactly the value of the friction coefficient, and in particular after that is built a finite element model, as you see here on the right, of the pin-on-disc apparatus, in which obviously we consider the load condition and the rotational speed condition. This finite element method is used for the calibration of the Archer wear model, and which basically is used for the evaluation of the wear process in general, for the volume loss due to wear between for the contact between the acetabular cup and the femoral head of the process. So the calibration consists in the evaluation of the two exponent m and n of the Archer law. And in particular, the input of the model of our model are four inputs. So H is the hardness of the material, K is an adimensional constant called Archer constant, and the two exponent of the pressure and the speed respectively. So basically the calibration is made in very simple way. So we varying these two value of speed and pressure until the difference between the volume transported from the pin that we know from the experimental apparatus is very similar to the finite element model. In this case, we reach this calibration for this two value with an error of 0.09%. So for the calibration we use this two exponent. After the calibration of the well model, the same process is applied to the processes model. In particular, this is our processes model, which is the well-known Charley model, which is very is commonly used because of its simple geometry. And in particular, we consider the load rotation condition, which came from literature research, and basically is an average between different clinical study of different patients. And also in this case, we build a finite element model. So as you see here, we consider the load condition and the rotation condition. And through the actual law, and obviously using the exponent that we find through the calibration, we evaluated the total volume lost due to air. Obviously, in this case, we considered only one instance, and we reported these results to 1 million of cycle, which corresponds to 1 year of gait, and we obtained this result that. Compared with literature results and clinical studies, is in very good agreement with other research. Enough. Thank you.
Thank you very much, Alberti. I have a question, and then I can ask to the audience other questions. So you use in your work the guide cycle. You consider this cycle. But in this cycle, you have also stage or phases of acceleration and deceleration, is correct?
Yes, in general, yes, the gait cycle is composed by different phases. In particular, I mentioned this in the full presentation. So, for example, the stand phase, etc. In general, yes, I have in function of the rotation and the position of the processes, I have a load on the rotation that can be obviously positive or negative. So in this case, I only consider the rotation, the value of the rotation, and in degrees and force.
Okay, because it is possible, I mean, to consider this variation of speed, for example, during this stage or phase of acceleration or deceleration in the model, or is not that process?
Yeah, in general, when I build the finite element model, for example, I can use the acceleration. Yeah, okay. It is one of the input that I can use. Okay. Basically, I use this for simplification because, for example, in the ANSYS, I use ANSYS for the finite element model, and one of the type of modeling is to use the angular position. So if I have already the information in degree, I use directly this information. But yes, obviously I can use also the acceleration.
Okay, interesting. There is any question from the audience? So I have a second question. Because at the end of your video presentation, you told that also a linear model can be effective to
in general
results. Exactly.
Yeah.
But in your opinion, is there any other type of movement in a prosthesis, for example, a torsion, or I don't know which type of movement that instead needs to be simulated through a non-linear model?
In general, yes, the linear model is in general the commonly used in the literature. I think that this is a novelty because from my research, I never find personally a non-linear model. But in general, the non-linear model is related to the contact between these two parts. I think that in general the force of the rotation are good for characterize completely the process. Yes, maybe we consider other movements such as torsion, And yes, but in this way, for example, for the moment with our research group, we developed a multi-body model of a human body, in which maybe can be considered this other type of motion. Yes, for the moment, I think that is a good basis, but yes, obviously it's possible to consider other movements.
Yeah, of course, it's more complex, but
yes, it's more complex. Yeah.
Yeah, thank you very much. Very interesting.
Thank you.
So, other question from Turin or from online? Okay, thank you again.
Thank you to you.
And we can progress further. So the next speaker, of course, can be more relaxed in their short presentation. I want to welcome Professor Fabrizio Greco from the University of Calabria, the Department of Civil Engineering, which will present the talk titled Stability Analysis at the Micro and Macro Scales in Periodic Bio-Inspired Composites.
Hi, I would like to say you that I'm Andrea Pranno. I'm one of the co-authors
yes.
because I'm a substitute of the Professor Fabrizio
Yes,
Greco.
Welcome, Andrea.
Okay.
So you can share the screen and take your time because we are well in advance respect to this.
Okay. Okay. Did you see my screen?
Yes.
Okay. Thank you. In this work, the interchange between the macro and the micro instabilities in acrylite composite materials has been investigated by examining the different combination of platelets volume fraction and aspect ratio and shear modulus contrast between the stiff platelets and the soft matrix. The excellent properties of these bio-inspired acrylite materials are based on the unique arrangement of stiff mineral platelets linked together by a soft organic interface in a brick and mortar scheme. The macroscopic stabilities analysis is performed in terms of loss of elasticity condition by monitoring the minimum eigenvalues associated to the acoustic tensor, while the microscopic stabilities analysis is performed by monitoring the minimum eigenvalue associated with the microscopic stability functional. The results highlight that the critical stability mode shapes, together with their critical load factor and wavelength, are highly influenced by the geometrical arrangement and the material composition. From a general point of view, the critical stretch ratio has an increasing trend for low volume fractions until reaching a peak, and then a decreasing trend for high volume fraction. In addition, high shear modulus contrast experience macroscopic instabilities at lower uniaxial compressive loading, which correspond to higher critical stretch ratio. For the investigated range of geometrical and material parameters, the instabilities are found to be global with an in-phase mode shape. It was also obtained that out-of-phase instability mode shapes occur at a significantly higher magnitude of homogenized energy compared to the in-phase one. The results indicate that adopting a small unit cell assembly, the microscopic stability analysis provide, in most of the cases, strong underestimates of the critical stretch ratio, and that an accurate stability prediction can be instead obtained by monitoring the strong elasticity condition, which is less expensive computationally than a rigorous macroscopic stabilities analysis. Thank you for the attention.
Thank you very much, Pranno. Is there any question from the audience in Turin or online? Okay, I can progress with the question.
Okay.
The presentation was really complex, I think, because the mathematical, the analytical development of the topic is really complex, and also the simulation, of course. But I would like you to shortly say what are, in your study, let's say, the stages that are absolutely necessary to go from the macro to the micro scale. So what are the theoretical steps that allow you to go from the macro to the micro scale, in short?
Basically, you can see in this slide, I performed two kind of simulation. I adopted a Compton multiphysics software with a subroutine written in Compton application builder. The first subroutine has been implemented to perform a macro instabilities analysis in terms of loss of elasticity condition. This is a widely used theory in literature to analyze the stability analysis in homogenized composite material, for example. Also, the solution of the principal path, how you can see here, is obtained. The homogenized tangent moduli tensor, which is the CR over sin here, is obtained by performing 4 linear perturbation, which is highlighted here in the slide. Then is solved an eigenvalue solve problem to evaluate the acoustic tensor. And the eigenvalue are monitored to understand, to detect the first stability at macroscopic scale. This is widely used in literature to evaluate the stability with long wavelength. While when we would focus on the microscopic stability, which is useful in composite materials which has a complex microstructure, we use a microscopic stability analysis. So a second subroutine instead has been implemented to evaluate in a sequential way for each loading step the minimum eigenvalue associated with the macroscopic structural stability function. The macroscopic stability, how you can see in this slide, was detected for an increasing assembly of unit cell because the macroscopic stability can be obtained by monitoring the strong elasticity condition. But when we are detecting the microscopic stability, we don't know the length of the stability, so we have to perform the analysis changing the dimension of the assembly of the unit cell. So I can see in this presentation, for example, that I changed the assembly to understand the exact wavelength of the stability. Okay. So,
so your hypothesis is to constantly or change these lengths several times.
Yeah, but how you can see from the computational point of view is too expensive. So this work is useful to understand which kind of stability analysis we can do in this kind of materials. So this research field is young, so we're trying to understand which one of these theory can be used for understand the mechanical properties of these materials.
Yeah, okay. Thank you. Very, very interesting and complex, really. But I have another question that is related with this first one. So as the field is new, what is, in your opinion, the most evident, clear for you, or evident from the literature, a field of application of this type of research? So why is it so important to be able to simulate both the macro and micro scale at once?
Okay, thank you for this question. This is really important because, for example, such kind of materials with complex microstructure are useful, are widely used for example, for the wave attenuation, for the tuning the wave propagation of the elastic waves. For example, with our group, research group, we are working on a study on this kind of materials where the onset of microscopic stability leads to a change the shape of the macro-like composite materials. So this pattern transformation influence strongly the wave attenuation of such materials. So from these preliminary results, I obtained that with such geometrical parameters and material parameters, the instabilities are global principally. So we understand that to detect the onset of local instability, we should insert the void inclusion, for example, in such microstructure. So in another work, we inserted the void inclusion, so we detect the microscopic stability, and we substantially we I don't know how we can say the propagation, the wave propagation in this kind of materials is really influenced by the onset of microscopic stability. So understand which are the geometrical parameters and the material parameters which influence the onset of micro and micro is really important from this point of view.
Yeah, absolutely, because it seems really promising. I mean, if you are able to simulate this, it's absolutely interesting. So thank you very much.
Thank you.
Is there any other question for Andrea? Okay, thank you again.
Okay, and, thank you.
Welcome. We can progress with the fifth presentation. The next speaker is Dr. Elio Matteo Curcio, that is a research fellow from the University of Calabria, Department of Mechanical, Energy and Management Engineering in Italy, that will present the talk titled Shape Memory Alloy Reinforced Composites, Functional and Structural Response Induced by Thermal Activation.
Yeah, do you see my screen? Do you see my screen? Okay.
Yes.
Okay, good morning everybody. I'm Elio Matteo Curcio and I'm very glad to show you our work, which title is Shape Memory Alloy Reinforced Composites, Functional and Structural Response Induced by Thermal Activation. This work has been done in collaboration with Stellantis company. The project is called DARIA and aims to develop an aerodynamic deformable surface that adapts its shape to the car's operating condition. Our team's purpose is to design the metal polymer interface, analyzing and overcoming some technical issues ongoing during the design. In literature, it is already possible to find examples of prototypes working in aeronautical field and others, which use SMA actuators. The common working principle is to cast SMA material inside the device. There are several properties the SMA material have, but the property exploited for the realization of adaptive surface is the shape memory effect. It consists in the recovery of residual pre-deformation downstream of a thermomechanical training. To design and simulate the complex SMA's behavior, a design tool was built. Starting from Brinson work, a thermal model has been introduced to simulate the jaw leaking. The idea is to simulate the interaction of complex systems with the SMA components. For example, pre-adhesion tests have been carried out in order to simulate the SMA wires adhesion to solve the problem of metal polymer integration. Another aspect to take into account is the cyclical activation of SMA's element. Preliminary test has been conducted and show mechanical properties degradation. Thanks to the design tool, some first prototype has been designed and tested. They work fine. Thanks for your time. Thanks for your time.
Thank you very much, Elio. Is there any question from the audience? Okay, so I really enjoy your video presentation because I think that is really innovative. I like this topic. And I have some questions. The first is this reversibility of this shape memory effect, because you say that you are trying to test this temperature activation, thermal activation in cycles. So can you explain something more about this reversibility, how it works under these different temperature cycles?
Okay, kind of material works with temperature. There is two states, lower temperature and high temperature. At high temperature, the materials is active, okay? When you increase the temperature, there is this recovery of the deformation. When the temperatures go down, the material could re-deform, okay, with a spring or another element. For example, the stiffness of the same material, the additional material. We use a lamina, okay. This element restrain the SMA element. If you want, I can
Yes.
share my presentation. Okay. Okay, for example, this is the working principle. There is this wire in molding in the element. When the material, when the element's bending, the wire is recovered, and there is the moment applied on the section. This moment acts to re-deform the elements, the SMA element. Okay, and when you reactivate this element with the temperature, there is another bending, and this is a cyclical event. Or in this case, with a mass, you can increase the temperature and the mass go up. When the temperatures go down, there is another deformation. There is this pre-deformation of the wire, and we have this cyclical in activation and decreasing of mechanical properties.
Okay, so you observe a decrease in the mechanical properties after several cycles.
About 20 cycles, but is really correlated with the temperature, the activation temperature. We activate the wire with Joule effect with the current.
Yes.
When the current is very high, there is a very high degradation.
Okay, so you need to control the current practically very well.
With this model implemented in Simulink, we could use a sort of PID or a controller to realize a deformation controlling the current.
Okay, understand. And about the modeling of this activation, let's say, are you able to also explain this degradation effect, let's say, after all this cycle, or is still at the beginning the work?
We are still at the beginning. We can simulate the deformation and the stress applied on the wire or small element.
And did you observe also other, let's say, spurious effect in the sense that, of course, you have the momentum due to this shape memory effect, but is the gravity force or other type of external factor impacting your shape memory effect?
We don't investigate this aspect now, but we investigate the hair influence on the shape. As you can see on the video,
yes,
in the presentation, we test these components in wind gallery.
Yeah, absolutely. I agree that this was my second question, because you are testing practically the prototype with this condition of high wind velocity, because at the end the application will be under that condition. And my question is, do you plan, let's say, to test also this material, let's say, in a wet condition? I mean, with a surface that can be wet under airflow, because possibly this could modify a bit the temperature, I think, because you can have evaporation and other phenomena that can a little bit decrease the temperature, and so create a problem of activation probably.
Around the wire there is this red material. It's a
Okay, so it's completely isolated and okay, yeah, understand.
Okay,
thank you. Any other question from the audience? Okay, very interesting, and thank you for your answer. So we can go on with the sixth presentation. The next speaker is the PhD student Umberto De Miaio from Department of Civil Engineering, University of Calabria, Italy, which presents the work title Finite Element Analysis of Concrete Cracking, a comparative study between a refined diffuse interface model and an embedded crack model.
Thanks, Professor Bertolin, for the presentation, and good morning to everyone. So this work is focused on a comparative study between two numerical fracture models. On the one end, the diffuse interface model is based on an inter-element cohesive approach, according to which interface elements are inserted a priori in a standard finite element mesh to simulate crack propagation. The four no zero thickness cohesive elements are governed by a mixed mode exponential softening law. On the other hand, an embedded crack model combines the well-known strong discontinuity approach, able to introduce a displacement jab in the finite element kinematics once a certain stress criterion is satisfied, and a cohesive zone model to simulate the cracking behavior along the discontinuity. These two models have been compared by analyzing the cracking behavior in concrete spacement subject to both mode 1 and mixed mode fracture and multiple crack propagation. The numerical results are in good agreement with both experiment and the numerical models. However, the prediction of the ECM model appear to be more accurate, especially in mode 1 fracture analysis, respect to the DIM model, which predicts a slightly stronger structural response due to the artificial toughening effect induced by the mesh. Contrarily, concerning the mixed mode analysis, the DIM seems to provide more reliable results, especially in terms of crack patterns. Finally, from computational point of view, the ECM requires more advanced programming skills respect to the DIM approach, which instead relies on a classical interface formulation, easily implementable in the most used commercial finite element codes. Thanks for your attention.
Thank you very much. So thank you for the very nice presentation, very well done. And it's interesting this comparison with these two models. So I can ask first if there is any question from the audience, otherwise I will progress with some questions. Is there any question? Okay, so I have a question about the mesh sensitivity that you have explained in your video presentation, the complete presentation. Can you discuss a little bit better what is the difference in terms of mesh sensitivity for these two models, and add some comments on this aspect?
Yes, yes. So during the ECM simulation performed with three different mesh, a coarsest mesh and a finest mesh. I noted that the loading in the loading curve predicted by the ECM model, there are some jump load in the loading curve. These jumps are associated with the insertion of very large discontinuity in the finite elements. But instead, in the simulation performed with the DIM model with the coarsest mesh, less accuracy of the predicted structural response is observed in this simulation. Because the adopted spatial discretization is not sufficient to capture very well the stress gradients within the process zone ahead of the pre-crack. However, the curve is globally in good agreement with the other curve. To better understanding the behavior, this behavior that is the load jumps in the ECM simulation, I had also plotted the kinematic energy computed by the ECM model, and it shows peaks of the energy in correspondence of the load jumps due to the dynamic effect induced by the explicit solver. Above all, when very large discontinuities are inserted in the finite element.
Yeah, this is very interesting, this last approach that you explained, because eventually you can modify the errors or correct the simulation.
Yes. For the DIM, I could change reduce the fraction energy employed in the analysis for obtain a right loading curve.
And so, just to conclude this discussion, let's say, is it true practically that this embedded crack model can be defined as mesh independent?
Yes, the ECM model is very independent of the size of the element of the mesh, respect to the DIM model.
Yeah, because in the DIM, instead, you have this problem with the coarser mesh, let's say.
Yes.
Exactly. Thank you very much. I have another question because you also present in the video presentation this concept of crack adaptability in the ECM model. So why is important?
Yes. This is an advantage of the ECM model respect to the intra-element numerical model based on the strong discontinuity approach, because it not requires sophisticated tracking algorithms to ensure the correct direction and the location of the crack and to enforce the crack path continuity. This is possible thanks to the novel strategy employing the ECM model based on a crack adaptability approach, according to which the direction of the principal stress direction is recomputed at each step of the simulation until a threshold value of the crack mouth opening displacement is reached. In this way, the brutal crack locking phenomena that is very frequent in the fracture simulation performed by intra-element approaches are avoided.
Yeah, so you can practically say that this model also is quite consuming in terms of computation, can be interesting for this aspect or feature. Especially because you have this possibility to follow continuously this crack pattern, let's say.
Concerning the computational effort of the analysis. The two models leads to a comparable efficiency, even if a detailed comparison in terms of analysis times is not be conducted in the present work, since this model were implemented by using two different commercial finite element software. COMSOL multiphysics for the DIM model and LS-DYNA for the ECM model. And also the related simulation has been performed on different machines, because this work is developed during my visiting PhD period in Politecnica de Madrid. However, for this simple simulation illustrated in this work, the time analysis is less of 10 minutes.
Less of, sorry?
Of 10 minutes.
Okay, good. So thank you very much for your answer. Is there any other question for Umberto? Okay, thank you again for the presentation and the explanation.
Thank you.
So we can progress with the last presentation, that is the seventh presentation. The next speaker is the researcher Natalia Kosheleva from the Russian Academy of Science, Institute of Continuous Media Mechanics, which presents her work titled on application of distributed fiber optic sensors embedded into material for the mechanical state monitoring of civil structures.
Hello, can you see my slides?
Yes.
Okay, good. Let's start. My name is Natalia Kosheleva. I would like you to present my work, which was done in the Institute of Continuous Media Mechanics of the Russian Academy of Science, entitled on application of distributed fiber optic strain sensors embedded into material for the mechanical state monitoring of the civil structures. That was done together with my colleagues, Valery Matvienko, Grigory Servaev, and Georgy Gusev. The aim of this study was to check the possibility of the use in fiber optics sensors embedded into the structure for the registration, the mechanical state of the structure at the different stages of its life cycle. During the production of the concrete sample, there was an attempt made to embed an optical fiber that doesn't contain additional protective packages except for the standard polyimide 1 coating. This, it was possible to avoid an additional recalculation of the strain values obtained from the fiber optic sensors, which is necessary to restore the real strain distribution picture in the controlled material. So the work was divided into parts. First part was devoted to the mechanical behavior registration during operation. The results of measurement of the distributed force, as you can see on the slides, and was compared with the point sensors based on the Bragg gratings and the results of the numerical simulation that shows the satisfactory agreement when the loading the finished sample. And the second part of the work was devoted to the defect registration using fiber optic sensors and the possibility of using this embedded distributed force for recording the appearance and the development of defect has been demonstrated. And to conclude, despite a number of limitations, the considered approach can be used for the various laboratory studies, despite the fact that fiber optic sensor didn't have any additional coating to protect it. So in the laboratory condition, we can use that. Thank you.
Thank you very much, Natalia. So very interesting talk. There are questions from the audience. Okay, so I have some questions for you, Natalia. So it seems that these distributed fiber optic sensors are very effective in locating defects because, of course, they are homogeneously distributed and can cover all the length of the sample. But I would like to know if did you observe in the test some asymmetric factor, in the sense that is important, in your opinion, the place where you need to insert the fiber, it needs to be symmetric respect to the section of the sample, or you need to locate the fiber in another position in the section of the sample to increase the probability to detect the defect?
In fact, it depends. As it was shown on the slides, there are two kinds of fiber optic sensor that we use in our study. The first one that we called point fiber optic strength sensors. Usually, it's really important where we locate them, because as we make some previous research, they can feel like, let me see like that, the defects when it's like about 5 radius of the sample around. So yes, so it's really important to make finite element calculation before you put it inside the sample when you are looking for some defect detection. For the second kind of fiber optic sensor that we call distributed, that is really homogeneous, and we locate them inside our sample. This is somehow we can feel it as we want, because it's have really long field of sensing, and it is we who put the small sensors to measure. So in this thing, when in fact that's happened, we cannot guarantee sometimes the linearity. Yeah, exactly, because you know the concrete, sometimes you need really precise it, otherwise it's like little by little they feel up or down. This happens, but in this case we can see where we put the sensor, so we can see this unlinearity and we can take it into account when we calculate it. And in this case, if we, let's say, really didn't feel it, and we feel the detect, we can feel it by the other points of this sample line that we put inside. So we just need to take it into account if there is no symmetrically line inside the sample. So this is a good point of using both system inside the samples. Yes.
So practically you use this point sensor for verification, let's say.
Let's say that, yes, because both of these systems have their advantages and disadvantages. For example, as we can see, the point sensor, it's really, they are precise. So we can really feel it really good if we in this location area of defect.
Around this volume.
But if we need just only to see, like, okay, somehow here we can feel some problem, it's better to use the distributed fiber optic sensors, because we can use their length, we can see the strain distribution along all the samples, so we can see all the things that happens during loading, during some sample formation. That's really good because we can understand the mechanical picture inside all the stages of it, from manufacturing till the operational load, and up to this we can use it like structural health monitoring system. And also it's good that we can put it not only inside like we did, but we can put it on the surface. Yes, we just need to understand which kind of glue or something like this to
yes, to attach,
to connect them, yeah, to avoid some kind of strain distribution from the surface to our sensors. And the only problem is to avoid their fragility. That's why a lot of scientific researchers, they use special additional coating in order to protect them. In our research, we were trying to avoid it because we want to look how they will survive without any additional code, to avoid these recalculations, additional laboratory measurements. In the laboratory, we really receive a good result, so we didn't have any break-ins, let's say like this. So you need just to be really precise and really careful, so that is possible.
Yeah, but this naked application of the fiber is very interesting. Probably it can work in some specific condition also outside. Probably not
We
in
hope.
a very wet
We hope.
climate, but you know, in other climate or in other condition can work.
Maybe.
Absolutely, yes. And you partially also answered to my second question, because I was interested also at this aspect of the service life of the sample. So as you insert immediately the fiber since the beginning of the cast, let's say,
yeah,
of the sample, it would be nice also to see, for example, some data elaboration in terms of times. So if you observe some differences of the backscatter signal, for example, over the time,
of course,
because of the drying of the sample or because of the conditions that were modified into the sample structure.
Exactly, you're totally right. We did it from the beginning, from the sample when we the cement mixture put in our mold, and we start to measure from the both system. In fact, we have a paper already published on this topic, and we really feel the interest and dependence. We see all these periods of sample formation, the first one, the second one, the third one. It's really so clear that we can follow it, and we can understand even how much technological strains, process-induced strains, we receive after we receive the good sample that we can use somewhere. So this technology even we receive as a result the smart material, like let's say like that, because when you put inside the fiber, when you see and you save the whole history of its formation, you can analyze this and you can feel the risk. Okay, this sample wasn't so good because it's too fragile or too hard or something like this. So on the end of when the sample formation, the technological formation is end, you can see how much difference on the samples, on the different parts you can receive. So you can analyze it. Okay, there was temperature, or there was too much water inside, or there is something with the this mixture bad. So this is really good.
Yeah, I agree, because with this fiber you can measure temperature, relative humidity, so you have an idea of the equilibrium moisture content of the material at any time, any instant, and this is absolutely interesting, because practically you know the exact time when you can substitute the material because of lack of performance. And this is very economic, effective, let's say.
Yes, exactly. We can see the exact point when it's good enough to start to make some experiments with it, or we can wait until this time is well gone. So it's really interesting to compare. And also, as you can say, as you said, that was right, we can economize some time and efforts, because we can do a little part of the different mixture of the samples in order to measure and after choose the correct one for properties that you need after use this sample. That's really good.
Yeah, thank you very much for the interesting discussion. Thank you. So we are now at the conclusion of the section. So I want to thank Professor Marsavina for his interesting talk, and also all the speaker and the participant for this useful and interesting and stimulating section. And I hope you have enjoyed it. So now it's, I think, time for the coffee break, even if we are a little bit in advance. And I leave the floor to Professor Iacoviello. Thank you very much.
Sorry, but I was behind the PC. Hi, and thank you so much, Chiara, for your help and your chairing for this session. And so for the people that is in the room, you are all invited for the coffee break. For the people in remote, you can enjoy your coffee break by your own, and we will meet again at 11 o'clock for the session 6. Thank you so much. See you later.
Thank you. Bye.
gracias. Okay.
Good morning.
Hi.
Hello.
Okay, I think I was muted. So you have 10 minutes for your presentation all together, 2-3 minutes for summarizing your work, and the rest is for questions and comments from the audience in remote and in presence. So we have 9 presentations. We can start with the first work, which is experimental test on vapor and gas permeability of concrete boxes. And the work will be presented. There are 1, 2, 3, 4, 5 authors. Who is going to present?
Yes. Okay, I'm here. I'm going to share the screen. Just a moment. You can see the full screen of my presentation. You can see the full screen?
Yes, okay.
Okay, so I can start.
Yes,
Good
please,
morning.
go ahead.
Good morning, everybody. Who speak is Mario Lucio Puppio, and together with other colleague from the University of Cagliari, we present this first step of experimental test on vapor and gas permeability of concrete boxes. This picture shows cracking of a concrete wall. This cracking is it depends from the property, the natural property of concrete, and is measured with an instrument, a micrometer, that consent to have an estimation of the crack. As you absolutely know, crack is the primary path for external agents that produce both degradation of concrete and of reinforcement. It is also the main cause of concrete permeability, particularly for gas and vapor. The second phenomenon that produces permeability is the shrinkage. And the aim of this work is to present the result of a first step of investigation on some experimental tests of 4 concrete boxes characterized by 4 different external coatings. The goal of this research is so to explore this field in order to limit the vapor permeability and to ensure tightness of the concrete walls. At this purpose, 4 specimens with approximately cubic shape are tested, and the mockup is arranged, as you can see, using some concrete cockpit, usually applied in water discharge management. So in the mockup, we can have the concrete cockpit, the concrete cover, and the manhole, usually used to inspect the cockpit. We sealed with mastic all the joints, as in this picture. The main characteristics is that I want to highlight is the wall thickness of the boxes that is very reduced, only 10 centimeters. In this picture, you can show the first step of the test setup, the preparation of the mockup. Each box is equipped with a pressure gauge that performs 2 conditions, 2 purposes. The first is to introduce the gas pressure, and the second one is obviously to measure the internal pressure of the gas that we introduce. The test consists to apply this nitrogen azoto with an internal overpressure to verify the leakage and to eventually pressure that we can guarantee. The first step of the test was, in fact, to identify the main area with the leaks. So the 4 mockups that are presented here are characterized by 4 different coatings with different commercial material. You can read here are polyurea, mineral coating with different color, epoxy primer, and epoxy cementitious coating. Here there is the manhole for the alimentation by nitrogen, and the joint is sealed with different technology depending on the coating type. During the first step that I reproduced today, the behavior of the mockup A was the best, with an overpressure, a small overpressure reached, and no signs of gas leaks. This table, in effect, summarized the first result of the experimental campaign. In terms of, you can see overpressure, tightness, and preparing. Preparing is the preparedness procedure. So you can see, for example, that for mockup A, skilled workers are required. From the other side, unskilled worker can apply the other type of coating. As I said, the best performance in terms of tightness is relative to the specimen A and C. A and C are the best with more reduced legs. The specimen C, in our opinion, can be suggested because of the very simply procedure of application of the external coating. No one of the specimen in this test, because of some limitation of the experimental campaign, consent to have a significant internal overpressure. But as I said, this result can be attributed to the very severe test condition. So in every case, a separation of the function of mechanical resistance of concrete and the tightness of coating of other elements is suggested in reinforced concrete structure. So the results of this experimental campaign show that mockup A and C can be effective with this purpose. And a point of strength, in my opinion, is the possibility to inspect an external coating with respect to an internal one, and to check by time this performance. Considering the limited thickness of the wall of the box tested, and the poor quality of the concrete, the coating of mockup A and C shows the relative best performance. And the critical elements are the joints. The joints are critical points that have to be surveyed with care and attention. In the application of the coating, in fact, play a very crucial role, the preparedness of the worker and the initial state of the surface of the concrete. So in order to ensure a good performance in time, a periodical check and inspection to measure aging and eventually singular condition of the coating is absolutely suggested. That's all. I would like to thank you for the attention. And I'm available to reply to your question. Thank you very much.
Okay, thank you for your speech. We have a couple of minutes for questions from
I have a question.
Yes, please.
Hello. First of all, thank you, Mr. Puppio, for your very interesting presentation. And I have a curiosity, though. What led you into this experimental campaign? I mean, what's the idea behind, what's the need behind these experimental tests? And also, in the last slide, you mentioned that about the practical applications. So, which are the practical applications, in your opinion?
Okay, thank you for the question. I can explain why we start to do this campaign. That is a first step of a more complete experimental campaign. The purpose is to ensure tightness for concrete work, in particular in the industrial fields. So in our experience, in some components of industrial or for short-time application or for long-term application, is essential that concrete wall can guarantee the tightness, the vapor tightness. The ongoing international code admit naturally, it's obvious that concrete can have some cracks and so some principal path to gas, to water and other elements. But with an external coating, it's possible to ensure, of course, best performance as in the pool or other element with water. The problem is that in the pool or other condition, we have an internal coating, not an external. So in this case, there is a pressure that is unfavorable for us. And this is the real reason because we start this campaign, and the company that sold us this product highlights the main problem, that is that the pressure in this case is internal and pushed out the coating. Mm-hmm. But we see that the performance could be guaranteed in some cases. I think that it's more important also to evaluate the aging of this product because of the solar radiation and other conditions that we can have in the industrial field, UV radiation and so on. But it's a promising application for the moment.
Okay.
Okay, thank you. Very interesting.
Thank you very much.
Thank you, Mario, for your speech and your answer. I think it's time to move to the next presentation entitled Accounting for Shallow Foundation Settlement in the Analysis and Design of Multi-Story Frame Buildings, Development of a New Software Package.
Good morning.
Good morning.
I want to share my screen.
Yes.
So, good morning, everyone. Our work is accounting for shallow foundation settlement in the analysis and design of multi-story frame buildings, development of a new software package. I want to present our program. We have developed a new software package based on finite elements method and capable of analyzing and designing of multi-story frame concrete buildings. This is the interface of our program. We can present the 3D model, the plan view of the structure, also the elevation view of the structure. After analysis, we can present all the external forces in the elements. For example, this is the bending moments in the elements in the 3D view and the elevation view of the structure. The new analytical function that have been implemented in our program is inserting the calculation of the settlements and inserting its effect in the analysis and design. For example, we can view the deformed shape of the structure according to the settlements. No, generally, when we use commercial softwares and we want to implement the effect of the settlements, we insert springs at the in the joints at the base level of the structure. These springs only presents the elastic settlements and or the immediate settlements in the base, and did not present the consolidation settlements, which occurs due to many years of time. In our program, we calculate these settlements in this method. We perform the analysis, and the program calculates the reactions at the base levels. And after that, the program, according to experimental relationships, calculates the all the settlements, the immediate and the consolidation settlements, and assign these settlements in the as translations in the base levels and reanalyze again. For example, if we want to view the difference between the two cases when inserting the when accounting the settlements effect and without accounting this effect, we can choose this beam in the structure, and if we enter the internal forces in this beam group, we can see here the bending moments without taking the account of settlements. And here, if we insert the account of settlements, we can see the big difference between the two cases, and also in the critical joints here, the joints where the connections with the columns, we can see here that also the moments flipped from positive to negative. From this work, we can see that the analysis accounting for foundation settlements effect can reveal inadequate soil characteristics to set up the buildings, and or can help to make a decision to change the type of the foundation. For example, in our buildings, in the example, we can't use the spread foundations. We have to use a slab, draft slab, general draft slab under the whole structure. That's all, and thank you for your attention.
Thank you, Anas. So now it's open for discussion. Is there any questions from remote audience or?
May I ask, Mr. President?
Yes. Hi, please.
Could you very shortly describe the novelty of this model? To my knowledge, there are commercial packages doing similar things. What is the main difference? What is the main novelty?
Yes, I said
to introduce a new one.
Yes, of course. First of all, our program is a new program for modeling, but
introducing a new model does not make it novel.
Only the function we are working to insert the consolidation settlements. The other programs, for example, CSI programs, only calculate the settlements according to the inserting springs in the joints at the base level. This is the elastic settlements, but they didn't calculate the consolidation settlements in in the base level, which is the major settlements. We calculate this by iterative analysis in our program.
Thank you.
Is there any other question? Maybe I can ask a short question regarding the way you model the soil, the deformability of the soil. Did you consider any interactions between the deformation in point to point? I mean, is it like a Winkler soil with a bed of spring or something else?
I understand. For this moment, we only calculated the translations at the joints, and we after the first iterative, we assigned these translations at the base joints and reanalysis again. We didn't insert the interaction between the soil and the basement.
But is it your software developed for linear analysis, or can you also perform nonlinear analysis?
We performed the nonlinear analysis for the beams. We assigned the hinges, plastic hinges, in the at the ends of the beams, and the program can present the nonlinear analysis using moment hinges, using fiber analysis for the section.
Okay.
Thank you.
Thank you. So if there is no other questions, we can move to the third presentation. Thank you again to the speaker. The third presentation is entitled Influence of Rock Inclusion Composition on Fracture Response of Cement Composite Specimens. There are many co-authors. I don't know who is going to present it. Maybe Mikael Willidal. Yes.
Yes. Okay, can you see it? Yeah.
Okay.
Okay, so
please.
I'm sorry for for problems. Thank you, Mr. Chairman. My name is Michal Vidal, and I will present you the influence of rock inclusion composition on fracture response of cement-based composite specimens. I hope you can listen to me, or you can hear me well. So, first of all, to determine the influence of the interfacial transition zone on fracture behavior of cement-based composite, especially specimen geometry was designed. As you can see in figure 1, it was a prism of the dimensions 40 times 40 times 160 millimeters with internal inclusion of the dimensions 8 times 8 times 40 millimeters. The inclusions were made of rocks, as you can see in figure 2. 4 types of rock inclusions were used. It was amphibolite, basalt, granite, and marble, which are typical rocks used in Czech Republic for the production of crushed stone. Photo micrographs of the rocks under study you can see in figure 4. In picture 8, you can see amphibolite, basalt, C is granite, and D is for marble. These specially designed specimens were tested in 3-point bending fracture test configuration. You can see the testing machine in figure 3 on the left, and detail of measuring equipment on the right of the figure 3. So the results of fracture tests, the load versus deflection, it means displacement in the midspan was measured. As you can see in figure 1, you can see there is a reduction in the maximal force value in the case of specimens with the inclusion in comparison to the matrix specimens or reference specimens, which was without inclusion of only matrix. After fracture tests, after fracture tests were performed, fracture surfaces were examined via nano-indentation technique. So Young's modulus E in the ITZ was measured or measured. So you can see it in figure 2, and also hardness H in ITZ, which is in figure 3, and also average creep compliance function AT in ITZ region was measured or calculated. So to determine the influence of chemical composition of rock on micromechanical parameters, we decided to simply use the correlation matrix. It's in table 1. Quite surprisingly, there is almost no strong or very strong correlation. It's mainly weak or moderate correlation. In table 2, you can see influence of mechanical fracture properties of rock on micromechanical parameters measured by nano-indentation. There is a strong or very strong, mainly negative correlation, except of Poisson's ratio of rock material. Influence of mechanical fracture properties of rock on overall fracture behavior of the test specimens, you can see in table 3. There is the same almost no correlation or no strong correlation in the case of Poisson's ratio of rock material. And finally, you can see the influence of micromechanical parameters measured by nano-indentation on the overall fracture behavior of the specimens. It's in table 4. And we can see that there is a very strong or in some cases perfect correlation. So it means that the micromechanical parameters of the ITZ has a strong impact on the final fracture behavior. So that's all. Thank you for your attention.
Thank you. We have some minutes for discussion. Is there any question from remote audience? Hello?
May I?
Yes, sure.
I observed scattering of the experimental results, and then you mentioned that you determined some properties by nano-indentation.
Yes.
If I understood correctly, the material is inhomogeneous, definitely inhomogeneous.
Yeah, the matrix is homogeneous, and
so this slide, yeah, the one with the scattering, what is the correlation between the curves drawn? The scattering is huge in previous slide.
You mean which
one? The previous one. You have some experimental points.
Yes, yes.
And some curves. Are the curves based on curve fitting of the experimental results?
Yeah, this
what is the coefficient of correlation between the curves and this cloud of points?
Yeah, it will be not much probably, but this power series were chosen because it's the same power series, but different were found in the case of porosity distribution. but of
I
course.
mean, do you feel safe to draw conclusions based on these curves, which are obtained from fitting of this cloud of points?
Pardon, yeah, can you speak louder, maybe, or?
I mean, do you feel safe using the curves obtained from fitting on these clouds of points? Why is it a power law and not a different one?
I said because
curves that could fit somehow these scattered points.
Yeah, the power law was chosen because some or we measured also porosity, and there was also power law, but with decreasing series. Or
I mean, what is R square, the coefficient of regression for one of these curves?
I'm sorry, I can say it. I can't remember.
Okay, thank you.
It will be not much. So it's not so good. Of course, I understand. It's
okay. Thank you.
Okay, thank you.
Okay. Is there any other question? I think otherwise we can move to the next presentation. Thank you again.
Thank you.
Thank you. So next presentation is entitled Study of the Durability of a Concrete Composite Mixed with Polypropylene Fibers.
Hello.
Hello. Good morning.
Can I?
You can share your screen if you want.
You can see?
Yes.
Yes. Thank you, Professor.
You can put in presentation mode.
Yes. In this presentation, I will take about study of the durability of concrete composite mixed with polypropylene fiber programmed in this conference. To respect the allotted time, I skipped the material and the method, experiment program, and the test protocol parts. So I focus on the results and the discussion. The results, several experimental tests were carried out in the laboratory. The composite was tested with different volume fractions of polypropylene fibers from 0.05% to 0.15%. As the reference states, the porosity of the various non-fibers and fibrous matrix is equivalent of an order of 30.2%. It's certain that the presence of polypropylene fiber in the cementitious composite results in the connectivity of the pores of the composite with the connect and consequently an increase in the pore volume. Here we can see the polypropylene fibers dispersed in concrete, and we can see the cavity and the pores. The accessibility of polypropylene fiber concrete increase with the percentage of fibers, which is explained by the fact that the adhesion between the polypropylene fibers and the aggregate form cavity connected to each other. For the effects of polypropylene fiber on the gas permeability of the composites, you can see in the picture that in the figure that we have a short increase of the permeability with the dosage of polypropylene fiber of 0.10%. The gas permeability increased by 1.34% on average compared to concrete without fiber. For the diffusivity of the composites, as with the gas permeability, there is a slight increase in diffusivity with the dosage of polypropylene fibers of 0.10%, approaching 6.25% on average compared to the concrete without fiber. For the part of effects of PP fibers on the fire resistance of the composites, the fire resistance test consists on measuring the compressive string after with the volume fraction 0.10, 0.13, and 0.15% in polypropylene fiber. When after the same current period, each group was exposed to different temperature, 300 and 600 degrees Celsius, and we measured the compressive strength. Here in the table, we can see the value of the reduced compressive string in the percentage at different temperature. So the conclusion that's for the temperature of 300 and 600 degrees, the composite with 0.15% exhibit the less loss in the composite string. This loss is accumulated for at 6 hours of exposure for the two comparison. So the percentage of 0.15% is the good dosage. And you will see the reduction is it's interesting compared between other fraction of volume. As you can show in the curve in figure E and B shows that the compressive string of the 0.15% polypropylene fiber composite remain in the order of 27 MPa against 20 MPa for concrete without fiber. It's written in the color green. As a conclusion, the durability was studied using the three main indicators. The analysis of the results obtained placed the concrete or fiber of polypropylene in the same class as ordinary concrete according to the Guide of French Civil Engineering Association. Second conclusion, under condition of very high temperature, the use of polypropylene fiber in the cement matrix reduce the effects of spearing and bursting of the concrete and consequently improves its durability. The optimal percentage of polypropylene to be used in the concrete for improving the fire resistance is about 0.50% by volume fractions. And the use of polypropylene fiber in cement use composites increase their performance in terms of fire resistance and can fund better development application in the civil engineering market in addition to its ductile nature. Thank you for your attention.
Okay. Thank you, Hassan. We have a couple of minutes for questions. Is there any question from the audience?
Hello, yeah, this is Mario. I have a question.
Yes, please.
Thank you for your presentation, very clear. And I just have a curiosity about your campaign test. Okay, do you speak about an increase of the resistance of the composites? And we see a very clear graph of the increase of the compressive strength. Okay, and yes, compressive strength is really better. And I would like to ask you if you investigate or do you think to investigate also the increasing of the tensile strength, and if you have to do some test about ductility. This is my curiosity, if you investigate or if you think to investigate this field. Thank you.
Yes, it's a good question. In my first work, I study the influence of fiber, polypropylene, and scissor in the ductility, in ductile property. So the results is that the fiber, the polypropylene fiber, increase the ductile property and limits the crack of limits the propagation of crack. So it's it's interesting for adding polypropylene fiber in the composites, semi-fused composites. In this study, we used the tensile string and compressive string and other measures for the results. But in this research, we are focused in the compressive string, and for 3% of polypropylene, 0.10 and 0.30 and 0.15%. And we can see in the table the degrees of the reduction in percentage between in different temperatures.
Okay. Thanks for it's okay for me. Thank you very much for your answer.
Thank you.
Are there some disadvantages of adding these fibers, or only advantages?
Yes, it's advantage to add fiber in the concrete because as you can see in the conclusion, it's interesting for the resistance, fire resistance. But in the durability, it's not interesting because because the result is not adding fiber in the composites creates the pores.
So there is a compromise between advantages and disadvantages.
I do height temperature. Yes, advantage and disadvantage.
Thank you.
Thank you.
Thank you, San. It's time to move to the next presentation. Thank you. The title is Exploring the Acoustic Activity in Marble Specimens Under Tension While Entering into the Stage of Impending Fracture. Is it Professor Kurkuis who is going to present?
Is the screen shared?
Yes.
Okay.
Okay, Stavros, please.
Thank you very much, Mr. Chairman. Thank you very much, Andrea. This is an ongoing research project. The main target of which is to check various sensing techniques which could be applied for structural health monitoring of cultural heritage monuments. So in this particular study, we pay attention mainly to study the acoustic activity in marble specimens in juxtaposition to the respective electric activity in order to have some points that could help us to comparatively study these two sensing techniques. You can see here the experimental protocol, very large plates of Dionysos marble with two symmetric notches. And on the one side of the specimen, we have acoustic sensors. On the rear side of the specimen, we have electric sensors, very close to the notches of the crown. Now, what is very difficult in these studies is that the activity is intensified during the very last loading stages. So there is a lot of information during the very last moments before fracture. So it seems that describing the results in terms of time is not very convenient. So usually we plot the results in an inverse time arrow, the so-called time to failure parameter, and mainly in logarithmic scales. You can see comparing these two figures that we have a better insight into what happens during the very last moments before fracture if we plot our data according to this inverse time arrow. Now, we focus attention mainly at the steps just before fracture. From a total duration of about 1,000 seconds, we focus attention at the last 20 or 30 seconds. You can see here that the acoustic activity, if described in terms of cumulative counts, seems to obey very satisfactorily a power law, which is already concluded when we describe this acoustic activity in terms of their function, as it will be seen later. It was very systematically observed for all classes of specimens with very little scattering. And what is more interesting, this power law starts governing the behavior of the notch from which fracture starts much earlier in comparison to the notch which did not cause fracture propagation from the tip of the notch. Then we focus our attention to the electric signals. You can see here the electric current recorded and the hits per second and the load. Again, you can see that what happens is mainly during the very last second. So again, we focus attention on this inverse time arrow. And you can see here that the acoustic activity, it is here described in terms of their function, just to emphasize that it does not play a crucial role whether we describe the acoustic activity in one or other parameter. And then you can see here the respective very last seconds before fracture, what the electric sensors described. Again, you can see that during the last seconds, we have a power law that governs the behavior of the material. So if we assume that when this power law starts governing the response of the material, it is a kind of pre-failure indicator, then we can relatively safely conclude that at least for the Dionysos marble, we have a very clear pre-failure indicator, which is provided almost simultaneously by both the acoustic sensors and the electric sensors. Of course, this is a study that used only specimens made of Dionysos marble, so I'm not in the position to safely generalize this conclusion. However, ongoing data, ongoing experiments with other materials seems to support this conclusion, and seems that it could provide us with an index that could be used when we are monitoring the structural health of ancient monuments, because the electric sensors are very small and do not harm the aesthetic splendor of the monuments. So this is very shortly my presentation. Thank you, Mr. Chairman, and I am here for questions.
Okay, thank you, Stavros, for your very clear presentation. We have some minutes for questions.
I tried to be very short.
No, it's perfect. We have 5 minutes available for questions.
I think
maybe
that the
I
most
can
important
start asking a question. Yes. So, no, well, I was going to ask you what is, in your opinion, really the precursor capacity of this method. Do you think it could be a tool which allows us to have like a warning anticipating the fracture?
This is our target, but it is very far from practical application because, as I mentioned, we have to check it for various materials. We have to take into account that most of the ancient monuments made of stone are cracked, so we have discontinuities, and it means that the signals will not be so clear as it is in a perfect specimen made of for laboratory purposes. But already we have some structural tests with epistyles from the Parthenon, copies of the epistyles, which are connected by metallic connectors, titanium connectors. Although there we have a much more complex system, it seems that, yes, both the F function describing acoustic activity and the electric activity could provide, I emphasize, could provide. It must be checked, of course, for additional materials and additional loading schemes. It is promising, but not definite.
Okay. If there is no question, maybe at the laboratory scale, I was wondering if you have tried to apply this acoustic emission technique to loading condition of different mode of fracture, like mode 2 or...
In fact, when connecting epistyles, the principal loading mode is shear, yes. And we have checked experimentally such a scheme. Yes, we have very interesting qualitatively similar conclusions. The main problem is the quantitative calibration of the techniques. For example, the electric signal measured is of the order of some picoamperes. And if we try to apply this in out of the laboratory, we have, as you understand, noise. In fact, this technique, the electric technique, started from attempts to make prognosis for earthquakes many years ago. It's not our invention. It's very old technique, in fact, 40 or 30 years back. However, the results are not generally accepted. We cannot make prognosis about upcoming earthquakes. However, the underlying principle exists. While we have microcracking, we have generation of electric signals. So if we somehow manage to calibrate these signals correctly against a mature technique like the acoustic emission one, then we will have an additional tool that could be used because it is very cheap and very easy. The setup is very simple and it's very easy to apply this technique.
Okay.
But not yet.
Okay, I understand. Okay, thank you, Stavros, again.
Thank you very much. Thank you.
Thank you. Bye. And we proceed to the following speech. Title is Limit Plastic State of Notched Solids with Properties Dependent on the Type of External Forces. There are two co-authors, Eugenie Lomakin and Boris Fedulov. Is there anyone of the co-author present? No? So maybe we can go ahead with the next presentation and try again at the end. So the next one is a cyclic elastic plastic SED framework for fatigue life assessment in notched components subjected to multi-axial loading. The authors are Branco, Costa, Prates, and Filippo Berto. Who is going to present? Hello? Who is presenting the next paper?
Что ж такое?
So maybe now we have, sorry, the speaker of the previous paper, limit plastic state of notched solids.
Yes.
Okay. Because I can't read Cyrillic characters, so this is why. So please, you can start.
Can you see my presentation?
Not yet.
Chairman.
No.
No. Черт. Что?
Maybe you can say a few words to summarize your paper, and we can see if there are questions.
Ну и что?
Can you hear us? Can you hear me? I think there are some.
There is a green button, Professor Lomakin.
There are some poor conditions. Hello? There is a green button at the bottom to share your screen.
Yes. I'll try. Can you see my presentation?
No, not yet.
Sorry, can I help you? I will try to explain in Russian if you like.
Yes,
okay.
Yes, Natalie.
Yes.
Okay,
Please.
sorry, we will switch to Russian. It will be faster. Just 5 minutes.
What I
Евгений
have to do.
Викторович, здравствуйте. Вот смотрите, у вас есть зеленая
да.
кнопка. Зеленая
Есть,
кнопка
я нажимаю
демонстрация экрана.
Я нажимаю
Вот.
ее.
И что происходит?
Ничего не происходит, я не могу включить презентацию. Здесь вот и нажимаю, здесь PowerPoint в качестве виртуального. Сама она не активна.
Вот смотрите, попробуйте зайти в PowerPoint на компьютере сначала, свернуть его, потом нажать зеленую кнопку и выбрать вот в этой менюшке вот ее.
Так.
Who is the speaker? Maybe you can help me to translate. Is Lomakin?
Unfortunately, I'm from another city. I just know the professor Evgeny Lomakin. That's why I was
No, but just I'm trying to understand if it's Lomakin or Fedulov.
Lomakin.
Lomakin.
Yeah.
Yes.
There is some trouble. I don't know why.
I
He
think,
switched the green button, but nothing happens.
I'm so sorry, but really we are running out of time. I'm afraid we have to move to the next.
Yes.
I'm sorry. Maybe if someone is interested to your work, can. Well, yes. Well, yeah. Okay. I can make a questions if you can answer on. I mean, if there are no connections problems. I had a look at your work, and it's about limit analysis. I wonder if you consider also yield functions which are pressure sensitive, like a Drucker-Prager criterion, or did you use classical von Mises or Tresca criterion? Now let's share. Did you hear me?
Yes.
Did you hear my question?
I'm here. We can see the presentation now, Mr. Chairman.
Yes. The problem is that we are running out of time, so if you, I mean, just comments on my question.
That's a pity.
I think we have some troubles with connections. I'm really sorry, but I think we have to move to the next presentation, Professor Lomakin.
Okay.
So maybe, I mean, all the attendants can watch your video presentation, and if they want to ask questions, they can write you emails later on. Okay. Thank you. So, we move to the next one, which is a cyclic elastic plastic SED framework for fatigue life assessment. Sorry. Okay, who is the next speaker? Is any one of the co-author, Branco, Costa, Prates, or Filippo Berto online? No. So we can go ahead. So maybe at the end of the session, we can come back to Professor Lomakin if we manage to interact, there are no connections problems. So we go to the next presentation, low cycle fatigue damage accumulation near cold expanded hole by secondary hole drilling data. And I think the work will be presented by Professor Matvienko. Is Yuri Matvienko online? Or one of his co-author, Vladimir Pizarev, Sviatoslav Eleonsky. No? So everything was working perfectly. Now we have three presentations missing. It seems that there is some connections problems with the Russian front. I don't know. So maybe I'll move on to the final presentation of the session, and then we try again to get in touch with the previous speakers. So the final presentation is the influence of aluminum casting alloys, chemical composition of the interaction with the 304L stainless steel insert.
Hello, Mr. Chairman.
Hello, Paolo. So
okay,
please.
Yes, I share the screen. Sorry, there is some problem with the share screen.
I think, yes.
It's not my screen.
Can I?
So if you want to start with the previous presentation, it is not a problem for me.
Yes, let me see if I can switch off the sharing of the screen of the previous speaker. No, I don't think I have a control of this. Let me see. Maybe now you can share your screen, Paolo.
Okay, now I can do that. Perfect. You can see my screen.
Yes.
Okay, so I try to summarize briefly this work. This is work by myself, Professor Fabrizi, Professor Bonollo, and Professor Berto. The title is The Influence of Aluminum Casting Alloy Chemical Composition on the Interaction with 304 Low Carbon Stainless Steel Insert. This work is developed in the frame of lightweight design, and we try to produce component obtained by B materials, B metallic materials, so-called compound casting. That is a component that was made by an aluminum matrix with an insert of stainless steel, a wire mesh of stainless steel, in order to increase the mechanical performance. So we try to study this component in terms of mechanical properties and metallurgical properties, with a particular focus on the interaction in the interface between the aluminum matrix and the steel, the insert steel. In particular, we try to investigate the effect of two different alloy composition, aluminum alloy composition, in order to investigate the influence, of course, of the alloy elements on the interface between the matrix and the insert. In particular, we use these two aluminum alloys as matrix. You can see the first is aluminum silicon 7 magnesium, and the second is aluminum silicon 9 copper. The difference, the main difference consists in the amount of silicon and of course also in the amount of copper. Silicon is well known to increase the fluidity of the alloy, while copper increases the mechanical properties of the alloys. Another element is iron. that is greater amounts in the second alloy. But iron introduces some intermetallic precipitate that may get a brittle fracture to the alloy itself. So this is the production of component. We design a mold. You can see this in the right side of this picture, the mold with the cavity that is the shape of dog bone samples. Inside it, we put the wire mesh, the steel wire mesh, and we poured the aluminum alloy inside the cavity with at the inner side the reinforcement. We also investigate the effect of heat treatments carried out at 550 degrees for 10 hours in order to understand if there are some interaction between the materials, the aluminum matrix and the steel induced by diffusions of elements. These are the main results, in particular result of radiography testing, and that showed a great amount of lack of filling porosity, and in particular a greater amount of lack of filling porosity in the first aluminum alloys compared to the second one. And in particular, in the first case, we found more or less 1.22% of lack of filling porosity compared to 0.76% of lack of filling porosity. And the difference is due to the difference in silicon content that made the alloy, the fluidity of alloy greater in the second case, in the second alloy. We also analyzed the interface by optical and scanning electron microscope. We observed some area in which we found a good metallic bonding, and in some other areas in which we didn't reach a mechanical bonding, a metallurgical bonding between, of course, the matrix, the material, the aluminum matrix, and the steel. After the heat treatment, we observe the growth of a layer of intermetallic compounds, as you can see in the right side of this, this picture. We identify these intermetallic compound layers as beta intermetallic and tau intermetallic by comparison with the previous result found in literature. In any case, the thickness of such compound was very high, and they behave as a brittle material, so they are not so good for the mechanical properties of the component of the component of the compound casting. These are the result of a mechanical test. We didn't found good result in terms of mechanical properties compared to the samples without the inserts. So the insert seems to weaken the material yes, it weakened the material, and this is because the insert introduced some lack of filling porosity, a lot of lack of filling porosity that weaken the mechanical property of the component. Regarding the interface between the aluminum matrix and the insert, after the heat treatment and after the fracture of the component, we observe a brittle behavior, and with some fragments of such intermetallic compound on the steel side and also on the aluminum matrix side. So the main conclusion, in my opinion, the main conclusion is this. This is the point zero, in my opinion, of these works, in which we can found different improvement that we can obtain in future works. In particular, we can increase the pouring temperature in order to increase the fluidity of the alloy and reduce the lack of filling defect that are the main cause of the low material properties, mechanical material properties we found in the compound casting. We can also investigate or optimize the parameter of the heat treatment in order to reduce the thickness of the intermetallic layer. We can also try to preconditioning the surface of the insert, the steel insert, for example, using copper coating or other material coating. And finally, last but not least, very important in my opinion, is to modify the geometry of the insert in order to avoid such lack of filling defects. And also, we can also modify, for example, the roughness of the surface in order to obtain a mechanical bonding between the matrix and the steel. So thank you for your attention. This is all for now.
Okay, thank you very much, Paolo. So we have time for a couple of questions. Is there any question from the audience online?
Yes, Chairman, if you don't mind.
Yes, please, go ahead.
Prof. Ferro, it's a very good presentation and it's a very good work. I have just only two questions. The first one, what is the type of the mold for the material that you used for this study? Also for the intermetallic layer, because we have done the same, I mean, very close work. We did it between the steel and the copper, and we found like the intermetallic, when we do, it was like a very brittle. When we do more investigation, we found this one is an oxide layer, not an intermetallic. So how would you sure about like the steel and the aluminum will have like, I mean, a very good like intermetallic, even if it is brittle? So I hope you under my two questions, and it's a very good presentation, and thank you.
Thank you very much. If I understood, your question is about the intermetallic, why we choose such kind of alloys for?
Yeah.
There is not a reason on the basis of our choice. This is what we have in our laboratory and
okay.
what we can found in our laboratory. So we try to do that as a first experiment, and we try and observe what can we obtain.
Okay, so it's a very good work, and I think I will contact you like off the book, so we have some work that we can done together. We have done the same work, and I think we'll use your experience and what we have here, and hopefully we can get something.
As I said before, this is the point zero. We understood a lot of very important things about these topics. So I can share with you better, in more details, what we learned about this.
Very interesting, Prof. Thank you very much.
You're welcome.
Okay. Thank you. Is there any other question? Maybe I can ask, you were talking about the geometry of improving the geometry of the metallic part, but what about the spacing of this grid that you are using? Is it,
yes,
is it something that you can I mean, try to improve or optimize somehow?
Yes, it was a square mesh grid with a space of 1 millimeter, if I remember. But in my opinion, we can change the geometry, not use a wire mesh, because in between the wire, there are it is difficult for the aluminum alloys to penetrate and to obtain a good feeling of the cavity, because in this way we obtain a lot of let me say defects. the idea is to optimize the geometry and use additive manufacturing technologies in order to obtain the best geometry for this kind of compound casting. In this work, as I told you before, we try with what we have in our laboratory, and we have a mesh grid made out of stainless steel. But a good work is, in my opinion, to optimize the geometry and use additive manufacturing in order to avoid this lack of filling zone between the matrix and the reinforcement. It's very interesting because we can add at the same time the advantages of additive manufacturing and at the same time the advantages of casting process.
Okay, yes, very clear. Okay, so if there are no other questions, thank you again, Paolo. So actually we have still 10 minutes to the scheduled time for the session, but I might try again to see if there are the missing presenters of the previous work. Yuri Matvienko, Vladimir Pizares, or Sviatoslav Eleonsky. Is there anyone connected? I'm talking about the paper entitled Low Cycle Fatigue Damage Accumulation near Cold Expanded Hole. No? And let me try again with the previous paper, a cycle elastic plastic SED framework from fatigue life assessment in notched components. Co-authors are Branco, Costa, Prates, and Berto. No. So I think Professor Lomakin was online, but we tried hard to interact, but there were really some connection problems. So I think there is no point to try again. So at this point, I think we can close the session. Thank you all the speakers and the attendants for the questions and the lively discussion, and see you to the next session in the afternoon. Thank you.
Thank you very much, Mr. Chairman.
Bye-bye.
Thank you very much. Thank you, Professor, for nice, charming chairman.
Thank you. Bye-bye.
Bye-bye.
Goodbye. Thank you.